So let me start with a brief review of very classical things about ordinary differential equations. So in all the talk, I'm going to consider a time-dependent vector field U on the Euclidean space. Actually, much of what I'm going to say is valid in a domain or in an n-dimensional manifold, but in fact, in a lot of places, the easiest setting is that of the periodic torus because it's flat and we don't have to worry about eventual problems that we might have at infinity. Okay, so the associated ODE is what you can actually see in this equation in red on my slide. Is the usual ODE, which is following a trajectory which is tangent to the vector field at every time t. So the very classical theorem that we study in our first years as undergraduate student in any university goes under the name of Cauchy-Lipschitz or Picard-Lindelöf, depending on the place. And it says that if U is Lipschitz in space, which means that there exists a constant such that the difference of the values of the vector field between 2 points at the same time is controlled by this constant times the distance between the 2 points. Then for every initial x that you specify as initial condition for the ODE, the red ODE that now has a dagger, there is a unique solution gamma sub x. And sorry, let me get here. Okay, and the other thing that we actually learned is that the solution in fact depends continuously on both the initial data x and the vector field u, meaning that if you vary both of them, these solutions will converge to the corresponding solution. And in fact, you can say much more if you bundle all the trajectories together into what is called the flow map. So if I define this function phi of t and x, which is telling me the point which you reach following a trajectory which solves the ODE and starts at time t equals 0 at the point x. And if you look at this map, you actually know that as you vary t, you get a one-parameter family of isotopes. So the theorem, the precise formulation of the theorem tells you that the function is continuous in t, and at each fixed t, you just get a map from, in this particular case, for instance, from the torus into itself, which is Lipschitz, and it has a Lipschitz inverse. And in fact, you usually can say much more, meaning that according to the regularity of U, the flow phi will be as regular as U is. So it's going to be C1 if you C1, K times differentiable, C infinity analytic, depending on whether you actually satisfy these assumptions or not. And as I said, phi is really an isotopy because, of course, if you are at time t equals 0 and you look at the value of phi at some particular point x, then you just get x. So phi of 0 dot is actually the identity map. Okay, so now the pivotal problem for this talk is whether we can draw up the Lipschitz regularity of the flow of the vector field and still get a meaningful theory. And in fact, we know, again, classically from a theorem from Peano that you just need the continuity of U to get existence of solutions to the ordinary differential equations. On the other hand, as soon as you insist in having uniqueness, you will see that it fails as soon as you go a little bit below this Lipschitz threshold regularity. You might maybe worsen the modulus of continuity by a logarithm, and there are some well-known conditions by Osgood on as much as you can, how far you can push that. But as soon as you go to something which is just Hölder continuous, for instance, if you have a square root, then uniqueness fails in a very bad way. So a typical example that you find in textbooks is the ODE gamma dot of t is equal to the square root of gamma of t, of modulus of gamma of t. But in fact, you get non-uniqueness as soon as you have an exponent alpha here, which is strictly less than 1. So let me just analyze a little bit better how non-uniqueness fails in this situation, just to make the argument that it's really, it fails in a kind of bad way, meaning that not only there are multiple solutions for the same initial data. But even if you were to select some solution according to some principle, you would not be able to actually build a natural global flow phi, which has the properties that we saw in the previous slide. So take, for instance, one of the simplest examples in which you can actually compute the solutions explicitly. So you take gamma dot of t is equal to 2 square root of the modulus of gamma of t in one space dimension. Now, if you take the initial datum x equals 0, of course, the solution which is identically equal to 0 is a perfectly fine solution. But even t squared is a perfectly fine solution. And then you can actually combine the two solutions by deciding that your gamma is going to be equal to 0 up to a certain time, t0. And then from there on, it actually starts off and goes away from 0 quadratically, like t minus t0 to the square. So you get infinitely many solutions for this initial condition. On the other hand, if you look at positive times, t bigger than 0, and you take a positive initial datum, then the solution is unique, and it's given by this formula, x plus t squared, which means that if you're actually approaching your initial datum from the positive side, you will converge to the solution t squared. On the other hand, if you actually start from an initial datum which is negative, then there is a unique solution, but only for a small positive time. And so here you get the explicit formula, and you will see that you reach the time t equals 0 in finite time, after which, of course, you can decide to follow, to stay put at the point 0, or to later on sort of take off and go into the positive side by taking this t minus t0 squared. So if I were to make actually a picture of how these trajectories look like, so here you have a pictorial illustration. So you have here the x-axis, here you have the t-axis, and here in these curves, I'm just keeping track of where my solution gamma of t stands at the time t. So you see, for instance, that if you start at the positive point x, you will then have a unique solution, which is this parabola over here. You see that if you are actually at time t equals 0, you have the solution which stays put in 0, but then, of course, you have an entire region which is filled from trajectories which you can build by staying 0 up to some time and then taking off and taking the parabola as your solution. And on the other hand, if you're actually on the left, on the negative time, on the negative initial data, you see that you will have a solution which hits the time t equals 0 in a finite, the point x equals 0 in a finite time, and then from there on you have the choice to stay on the time axis or to sort of get off into this no man's land. Of course, then if you take a snapshot of what your flow map should be at a positive time t, you will see that there is this segment over here which is filled from points which are originating from trajectories starting at time t equals 0. So even if you choose a unique trajectory over here, for instance, if you choose to be the trajectory which stays put in x equals 0, your map will not define a homomorphism from the real line into the real line. And so the fact that there is a non-unique trajectory also cannot be remedied if your goal is to actually build a flow of the vector field, which is kind of preserving the previous properties. Now, why should you actually care of dropping the regularity of a Lipschitz when you want to solve ODEs? Well, one obvious motivation is that if you take the evolution of a fluid or a gas, it is actually a quite common experience that these evolutions might develop singularities. And here in this slide, I'm giving some examples like, I don't know, shock waves or detonations or cavitations. Nonetheless, even if the velocity field described by the particles of the fluid or of the gas is not regular, you still may want to actually follow the particles' trajectories. And this is a kind of bad news because compared to the example that I gave you, the vector fields that you're dealing with in these examples are typically discontinuous. And we saw that something bad happens even if you're actually continuous, but just a little bit below Lipschitz. And you're far from being Lipschitz, in fact. On the other hand, Some good news is that you don't maybe want to track all the particles, but you most likely want to track only some particles, meaning that if you have a set of measure 0 of particles, on the other hand, they might not be so important. And in fact, you have even more good news. If you're looking at a problem from mathematical physics, you actually are guided towards how you want to solve it by taking into account that often the singularities are just, I mean, the singular fields are just a model. Maybe what really actually the field is something which has very sharp transitions between two states. So maybe just being singular just means that the smoothness, that derivatives, for instance, are very high. Or on the other hand, you might actually be interested in smoothing out your singularity, and then what you really want to understand is the asymptotic behavior of the flows for the smooth approximations. Okay, let me still go a little bit further with the classical theory. There's a famous classical theorem by Liouville, which goes as follows. So if you take the Jacobian determinant of the flow phi, which is the determinant of the x derivative of the map phi, which is of course related to the distortion of the area when you compose with your flux phi. Then the theorem of Liouville tells you that if U is differentiable, the time derivative of the Jacobian determinant is equal to the Jacobian determinant itself multiplied by the divergence of the vector field evaluated on the flow phi. So this means that as soon as you know that the divergence of the vector field is bounded, then the Jacobian of phi stays bounded and also bounded away from 0. In fact, since you remember that the Jacobian of phi at time 0 is identically equal to 1, because the flow map at time 0 is actually the identity, a simple application of Gromov's lemma tells you that the Jacobian of phi is bounded from below and from above by an exponential. And in fact, you can say even more in case the divergence of U is equal to 0. And this is maybe what most of the people know as Liouville theorem. So if the divergence of U is equal to 0, for instance, if the vector field is Hamiltonian, then the flow phi is in fact measure preserved. So let me for the purpose of this talk, for future use, let me actually give you a rather elegant formulation of Liouville's theorem, which is using measure theory. So as already mentioned, the Jacobian determinant of the x derivative of phi is related to the change of variables formula when you're integrating the composition of a function f with the function phi. So this means in measure theory that if you consider a measure mu and you take the push forward of this measure, which is defined as simply integrating against the measure a test function f, but composed with the flow itself, then you can actually rephrase the Liouville's theorem in a measure theoretic way, and it works even if U is Lipschitz. So if U is Lipschitz, you take the flow of the ODE and you push forward the Lebesgue measure on your torus or on your domain of Rn, then you know that this push forwarded measure is actually still a density times the Lebesgue measure. And if you call rho the density, then this function rho satisfies the so-called continuity equation, which is a partial differential equation that you see over here. So the time derivative of rho is equal to the divergence of rho times U. And of course, as at time 0, the push forward of the Lebesgue measure is the Lebesgue measure itself, because the flow is the identity. Rho at time 0 actually starts being identically equal to 1. And you will see that the derivation that the map phi is measure preserving when the divergence of U is equal to 0 comes out of a very simple computation. So first of all, you can actually compute the divergence of U times rho, as I've done over here. And since the divergence of U is equal to 0, this is simply equal to U times the gradient of rho. And then this means that the continuity equation reduces to a kind of similar equation, which is called transport equation, which is written over here. And a nice feature of the transport equation is that, as it is classically known, the corresponding ODE is actually the characteristic equation for this transport equation. And this means that a solution is usually transported along the flow. So it's constant along the trajectories of the ODEs. In fact, this is a very simple computation. If you compute the time derivative of the function of the scalar rho composed with the field, with the flow of the vector field, well, you will get first the time derivative, which is hitting the slot, the time slot. And then when it's hitting actually the X slot, you need to use the chain rule to compute it. And this is like the full derivative. And now you can use the fact that the flow solves the ODE to replace the time derivative of the flow with the vector field U computed along the flow. And now you recognize that actually the flow phi is composed with each of the functions which are entering this expression. And so you can rewrite your time derivative as the expression which enters into the transport equation composed with the flow phi. And this being equal to 0 for a solution of the transport equation, you just get the conclusion that rho is constant along the characteristic curves. Okay, so now you might note actually, so now we are transitioning to kind of what I will call the modern theory. So you might notice that divergence of U bounded, if you are in one dimension, actually corresponds to have U to be Lipschitz. And this means that all the textbook examples that we have seen, like, you know, gamma dot equals square root of gamma, actually disappear. Nonetheless, when you actually go into more than one space dimension, an assumption like divergence of U being bounded, which formally through Liouville's theorem tells you that the Jacobian determinant of the differential of the flow should stay bounded, or even just assuming that the divergence of U is equal to 0, well, these assumptions actually cover a lot of interesting singularities. I mean, for instance, in incompressible fluid dynamics, the divergence, the condition divergence of U equals 0 would just be for free from the basic equations that you have. Now, in this talk, I will be typically interested in maps U, which are singular, in vector field U, which are singular, but not too singular. So typical examples are vector fields which are Sobolev, so which have one derivative which is in LP, or in the case in which P is actually going to 1 on functions of bounded variations, which means that I'm assuming that the vector field U has a distributional derivative, which is a Radon measure, which is a kind of better behaved space than W11 from some functional analytic point of view. And as I mentioned, somehow to avoid technicalities about plus infinity, I will assume throughout the rest of the talk that in fact my domain is the periodic torus, although a lot of things actually can be said for other domains. Okay, so why would you actually be interested in Sobolev or bounded variation vector fields? Well, Sobolev vector fields actually allow for a lot of the typical singularities that you encounter in mathematical physics. For instance, functions of bounded variations can be thought as a natural generalization of functions which are piecewise smooth and discontinuous along hypersurface. So a shear flow in particular would be automatically a function of bounded variation. So there's a very well-known theorem which has actually opened the door to a lot of applications in PDEs and some very nice applications in mathematical physics, which is due to DiPerna and Lions in 1988, and which was improved by Ambrosio in 2002. So the DiPerna-Lions theory in 1988 says that if U is a Sobolev vector field, and I don't want to be too precise, but the Sobolev regularity has to be taken in space, and the regularity in time is not really important, and the divergence of U is bounded, then there exists a reasonable, but just measurable, notion of flow for the ODE, which is unique and stable under approximations. And the result of Ambrosio actually covers the case of functions of bounded variations. DiPerna and Lions were not able actually to cover that case, but they could push their theory until W11. Now, not only it tells you that the flows are actually unique and they're stable under approximations, but in fact, the space of flows for such vector fields, so space of flows of vector fields over which you have a uniform Sobolev control and a uniform control on the divergence, on the L-infinity norm of the divergence. In fact, these flows are actually locally compact in the strong L1 convergence. Okay, so now what do I mean by reasonable flows? So DiPerna and Lions had an axiomatization back in 1988, but I'm following over here in these slides actually Ambrosio's axiomatization, which is in a sense easier to phrase and more elegant. So first of all, I insist that the map phi is, at least in some sufficiently weak sense, a solution of the ordinary differential equation that I'm interested in. Okay. So here there's a small typo in this. So here you should read that the map T, which goes into gamma of T, so this is a curve. I keep X fixed and then I vary T. So this actually has to be an absolutely continuous curve. Being an absolutely continuous curve, it is differentiable almost everywhere. And then I impose that gamma at time 0 is equal to X. That's the initial condition. And that it solves the ODE, which I'm interested in, which is gamma dot of T equal U of T gamma of T for almost every T. So now here you recognize that the absolute continuity assumption is kind of the minimum assumption that you want to rule out sort of strange situations in which being a differentiable almost everywhere is not really enough. So for instance, the step function would be differentiable almost everywhere, and the differential would be equal to 0 almost everywhere. Nonetheless, the step function is not constant. So now if you have an absolutely continuous curve whose differential is equal to 0 almost everywhere, then actually you would conclude that that curve is constant. And this property is kind of, in a sense, fundamental to establish or to hope to establish some uniqueness theorems for the solutions of the ODEs. Okay, so far so good. This just tells you that phi is a reasonable flow, even though I'm assuming as little regularity as possible. Now, the third assumption is more about how all these trajectories actually bundle together in this map phi. And it's the assumption that when I push forward the Lebesgue measure, I still find something which is bounded by a constant, which is uniform in space, but not in time, times the Lebesgue measure. So now this one was something that we were able to actually conclude from Liouville's theorem in the case of a Lipschitz vector field, and in the case of Sobolev vector fields, we were actually sticking it in as an axiom. And maps satisfying A, B, and C are called regular Lagrangian flows. And of course, you might ask a very natural question right from the beginning, which is whether this axiom C is really needed, or whether, as it happens for the classical theory, you could actually recover it from just being a solution of the ordinary differential equation, so just by satisfying A and B. And part of this talk actually will revolve around this question. Okay, so the modern theory also gives you the same PDE-ODE relations that we already saw in the classical theory. So first of all, it tells you that a solution of the transport equation and a rather weak solution of the transport equation, I just actually need to assume that rho is sufficiently summable, and I will actually just give you more details about this assumption later on. So you solve actually the transport equation if and only if you're constant along the flow. And similarly, you have a counterpart of the Liouville's classical theorem. So rho actually solves the continuity equation rather than the transport equation if and only if the measure that I build by declaring rho to be the density of that measure, which is absolutely continuous with respect to the Lebesgue measure, of course, is the push forward through this regular Lagrangian flow phi of the measure that you can build by taking the density at the initial time t equals 0. And once you actually have this theorem, it's rather obvious that if the divergence of u is equal to 0, then in fact your regular Lagrangian flow is measure preserving. So maybe I should have mentioned this before. So in the axiom, you're actually just requiring that the push forward of the Lebesgue measure stays bounded. On the other hand, once you've actually built up the whole theory, you will be able to give the usual exponential estimate for this function c of t, which is giving you the upper bound for the push forward of the Lebesgue measure. And in fact, you will also be able to gain a lower bound by the same argument. Okay, so now we were talking about solution of the transport equations and of the continuity equation. Well, the solution of the continuity equation is understood in a distributional sense. So in particular, I have an assumption on the density rho, that is essentially LP prime, and which is kind of on the dual exponent of the summability that I am assuming for U, so that actually the product of rho and U is an L1 function, and I can understand then all these derivatives in the sense of distributions. It's a little bit less clear what is happening actually for the transport equation, but this is a computation that we already had. If you take the transport equation and you take actually the advected part of the transport equation, you can rewrite this as the divergence of rho U minus rho times the divergence of U. And now again, you can understand solution in the distributional sense because rho times U actually makes sense. It's a summable function. But according to our assumptions on the derivatives of U, even if U, for instance, were a function of bounded variation, we are actually assuming that the divergence of U is bounded or it's even equal to 0, which means that the function, the distribution rho times the divergence of U is actually well defined. So in this sense, we will understand solutions of the transport equations. And now, what do I mean by stability? Well, there is stability in the following sense. If you have a Sobolev or a BV vector fields and you have a sequence of Sobolev vector fields which are converging strongly in L1 to your given initial vector field U, then the regular Lagrangian flow will also converge in L1 strongly to the final regular Lagrangian flow. And the compactness is a similar statement. So of course, if I have some uniform control of the Sobolev norms of a sequence of vector fields UK and some uniform control on the divergence of the UK, then I will be able to use the compacted bedding of W1P into LP to extract a limit, which is still a Sobolev map. And then I can apply the continuity theorem upstairs to just imply that the sequence of flows is actually strongly precompact in L1. Let me give you a crash course on how actually you prove these theorems, especially in the DiPerna-Lions original paper. Well, first of all, it's a kind of funny that, in fact, you don't derive the well-posedness of PDEs from the well-posedness of the ODEs, but you actually argue rather the other way around. So you focus on the transport and continuity equations, and you actually derive existence, uniqueness, and stability for them. And then after that, as a consequence, you actually derive existence, uniqueness, and stability of the regular Lagrangian flow. So let me give you a sketch when the divergence of U is equal to 0. So if you were concerned about existence, what you could do is something very silly. So you first regularize your vector field U, and you regularize your initial data, and you take, for instance, the continuity equation, and you solve it. You then use the classical theory to infer that these solutions, which would be smooth, have a uniform bound on the L infinity norm. And that's just because they're constant along the characteristics. And once you have this, of course, you can extract by weak star compactness of L infinity a sequence which is converging weakly star to some rho. And then you just use classical functional analysis to pass into the limit on the product rho epsilon times U epsilon, because U is regularized by convolution, is actually getting to the limit strongly. So in this way, you actually gain a weak solution. And you might notice that I'm not even using the Sobolev or BV regularity to do this. Now, what is much more interesting is how you prove uniqueness. So you would like to prove uniqueness by first establish the following fact, which is formally correct, or which would be correct if the solution rho were smooth. You would like to prove that if rho is a solution, that the composition of rho with any test function is actually a solution. And this is not easy. This is like the hard analytic part of the proof, if you want. But if you take into account that you're able to do this, what you can do at this point, you can use linearity to reduce the uniqueness to the case in which initial data is equal to 0. And then you observe that if you have initial data equal to 0, and you have a solution, since the modulus of this solution is also a solution by this property upstairs, which is usually called the normalization property in the DiPerna-Lions theory, you can simply integrate in space. And if you are, for instance, on a torus, this would be really easy. If you are on the whole space, you have to assume something at infinity. But once you integrate in space, you actually derive that the time derivative of the L1 norm of rho is equal to 0. And since at initial time it was equal to 0, you just conclude that rho was identically equal to 0. And that gives you the uniqueness. Now, it's much more subtle how you actually prove this renormalization property. So first of all, you smooth the equation by, for instance, convolving the equation with a smooth kernel. Now, of course, this is not anymore a PDE because here you have the convolution of the product, but not the product of the convolutions. So what you do is say that you put on the other side the product of the convolution of the product, and then add and subtract the product of the convolution over here. So now here on the left-hand side, you have something which is essentially the transport equation, or the transport equation part for the regularized smooth vector field U convolved with phi epsilon. On the other hand, on this right-hand side, you don't have 0, but you have a commutator type object. So let us call that commutator T epsilon. At this point, once I have this commutator, I might actually multiply both sides of the equations by the derivative of my test function beta, computed on the convolution of rho with the kernel phi epsilon. And then you recognize on the left-hand side that this is nothing but the transport operator applied to beta of rho star phi epsilon. Okay, now if I were to send epsilon actually to 0, and I were actually and I were able to show that this commutator on the right-hand side converges to 0, then in the limit I would actually get the identity that I want, that is that the time derivative of beta composed with rho plus transport part applied to beta composed with rho is actually equal to 0, which is exactly what I wanted to conclude. So now this part is rather simple for Sobolev vector field. I mean, it's like it follows from standard Sobolev space theory. On the other hand, it's actually quite a hard fact for BB functions, and this is where the proof of Ambrosio somehow had to wait 14 years to cover actually the BB case compared to the DiPerna-Lions theory. Okay, so now how do you get stability? Well, stability is rather easy because as we noticed in the existence proof, we actually have weak star compactness. So if you take a sequence of vector fields and you solve the corresponding PDE, for instance, the corresponding transport equation, then having a uniform L infinity bound for the transport equation, because it's transported along the characteristics, I can actually extract a subsequence which is converging weakly star. And then again, I can pass into the limit in the equation. Now, the renormalization property, though, tells you that if you're Sobolev in the vector fields, then also beta composed with rho k is a solution, and beta composed with rho is also a solution. And of course, having weak stability, you just would conclude that beta of rho k is converging weakly star to beta of rho for any test function. And now a property like this, of course, upgrades your weak convergence, your weak star convergence, to strong convergence, and hence to strong compactness of solutions to the PDEs. And now, once you have actually strong compactness of the solution of the PDEs, you can imagine you have essentially compactness of the flows because of this relation that you have, that the push forward of the Lebesgue measure through the flow is actually a solution of the continuity equation. So if you want, this is somehow some disguised, in some disguised way, the fact that the components of the flow map phi are solving some type of PDEs. Okay, so now let me get after this and say like to something which starts being like postmodern. So Bressan in 2002, because of some applications that he had in mind to PDEs, actually he asked the following question: can we quantify the compactness of these flows? And he gave a conjecture with an explicit rate. So now, just to just motivate you some results which came after his conjecture, let us look at the classical proof of uniqueness of the solution of the ODE. So let me now assume that I'm back into the situation in which U is Lipschitz, and that I have two different trajectories which are solving the ODEs, and they're starting at the same initial point at the initial time equals 0. Now, if I want to compare the two solutions, of course, what I can do and what is very natural to do is to take the modulus of the difference between the two solutions and differentiate this in time. Okay, so there's an obvious inequality which tells you that this is less or equal than the modulus of the difference of the time derivatives. And then I can use actually the ODEs to write the difference of the time derivatives. And here, actually, this should have remained less or equal then. So this is a typo. So now I'm looking at this estimate, which would tell me that the time derivative of gamma of t minus gamma bar of t is less or equal than the difference of the flow computed at the corresponding points along the trajectories. And now, if I had a Lipschitz regularity, I would be able to control this red expression with a universal constant c, which is the Lipschitz constant of your vector field gamma, of your vector field u, times the difference, the modulus of the difference between gamma and gamma bar at time t. And of course, now here you recognize Gromov's inequality, and the classical Gromov's lemma tells you that gamma minus gamma bar is identically equal to 0 because you started with gamma minus gamma bar being equal to 0 at time 0. Okay, so what can we do if instead of having a Lipschitz vector field, we have a Sobolev vector field? Well, of course, we can get up to this thing over here, which because of a typo is actually should be an inequality. And now there's a classical fact in the theory of Sobolev functions that you still have a Lipschitz type estimate where I cannot afford anymore to have a uniform constant. After all, if I had a uniform constant, I would actually be W1 infinity, so my derivative would actually be an L infinity function. But I can replace that constant by the maximal function of the derivative of the u, with the drawback that the maximal function now has to be computed at the point gamma of t and at the other point gamma bar of t. So of course, this is now not anymore something which is maybe nice, because the trajectories gamma and gamma bar might go through points where the maximal function of the modulus of the derivative of u is very high. On the other hand, you can actually have the heuristic that if you have two regular Lagrangian flows and you're looking at the trajectories of these two regular Lagrangian flows, most of the trajectories will actually not go through bad points. And so for most of the trajectories, I will be able maybe to bound this function of time in L1, and then deduce still uniqueness from Gromov's argument. And in fact, this approach can actually be taken, and it was taken by Gianluca Crippa and myself in 2007, and gives a different derivation of the DiPerna-Lions theory, at least in some assumptions. So for instance, we are not able to cover Ambrosio's BV theory. On the other hand, what is interesting is that later works by Gianluca and Francois Bouchu actually were able to cover, by using these ideas, situations which are not covered by the original DiPerna-Lions theory. So the two approaches kind of are neither a subset nor a superset of each other. So they're, for the moment, not compatible. Okay, so on the other hand, Bressant's conjecture rate, which was really for BV functions, we were only able to prove it for W1P with P bigger than 1 because of this maximal function estimate, which does not behave somehow so nicely when you're in the L1 context. And let me give you an interesting theorem that you can actually derive from our estimates. So this is a kind of Luzin approximation property, which tells you the following. So if you take, and it can actually be stated as an a priori estimate. So it's interesting, even if you take a smooth, and it's interesting and new, even if you take a smooth vector field. So it tells you that if you take, for instance, a smooth vector field and the corresponding flow phi, and if you give me an epsilon bigger than 0, I'll be able to actually throw away a set k, which has a measure less than epsilon, and I will be able to estimate the Lipschitz constant of phi on the complement of this small set with something which is uniform in the LP norm of the derivative of u, even though it's kind of crappy because it has this exponential in front here. And this was worked actually later. It was worked later on by other people. And here you have some references that it means that in a suitable sense, your map phi has a log of a derivative. I mean, for instance, if you take the Fourier transform of phi and you multiply by the log of 1 plus the modulus of the frequency, you will actually get a function which is in L1. So you will recognize that this is weaker than being in any fractional Sobolev space, kind of tells you that it has a logarithm of a derivative. And in fact, this is equivalent to taking, for instance, some Gallardo semi-norm definition of a log of a derivative. And quite surprisingly, it was later on proved by two group of people under some assumptions. I think the most general theorem is actually due to Alberti, Crippa, and Mazzucato, which came a little bit later than this paper by Yao and Schlatos. And actually, these results, they tell you that even though they look very crappy as an estimate, in fact, the rates that we get from this theorem are optimal for the compactness of the flows phi. Okay, so now let me get to the last part of the talk. So one non-rigorous interpretation of the DiPerna-Lions theory that you might hear actually often is the interpretation that the DiPerna-Lions theory tells you that for a Sobolev vector field, the ODE is well posed for almost every initial point, right? So if you were Lipschitz, you would know that for every initial point, there is a unique solution. And essentially, the DiPerna-Lions theory is telling you that there is a unique solution for almost every initial time. Now, except that, if you remember my axiomatization of what is a regular Lagrangian flow, we had 3 points, and 2 points were really that you were a reasonable solution of the ODE. But the third point was also that you had to be able to bundle all the characteristic curves into a flow which had a particular property, which was not derived from the ODE. So, in a sense, the question whether the DiPerna-Lions theory is really driven by almost everywhere uniqueness of the solution of the ODE in the classical sense was still open until just this year, essentially. And let me give you right away the answers actually that we got in the last couple of years. So first of all, there's a positive answer, which is due to a paper by Caravenna and Crippa, in which they use an argument suggested by Jabin. And in this paper, the two authors actually show that, in fact, if U is in W1P and the summability of the derivative of U is really larger than N, so if you embed, in particular, in Hölder functions by Mori embedding, then actually it's true that the trajectories of U are unique for almost every initial point X in a classical sense. Okay, but then we had a negative theorem, which is kind of surprising this year. And this is joint work with Elia Brouet and Maria Colombo. And the theorem says that whenever you have P less than N, you will be able to find a divergence-free vector field U, and which has a closed set of positive measure A of initial points, such that for every point X in this set A, there are at least 2 trajectories of your vector field U. So 2 solutions of the ODEs starting from that point. And the example can actually be made continuous, and there's a PhD student of mine who's writing the details over here, so that you would actually fall into Peano's existence theory. So for every point, you would have at least 1 trajectory, and you would have a set of positive measure of points for which the trajectories are not unique. And we are still, we still don't know exactly what happens in the critical case P equal N. If I had to bet something, I would bet on the fact that it's probably following into the category of the second theorem, so it's a negative answer. On the other hand, if you make actually a small improvement of Ln, a small logarithmic improvement, and for the people who are experts in this, what we need is that the derivative of U is in the Lorentz space Ln1, then actually almost everywhere uniqueness holds. And in fact, you could recover then the Jabin Caravenna-Crippa result from this one, which is strictly stronger. Okay, so let me just give you some comments about this kind of nasty non-uniqueness result. So you might remember that we had this regular Lagrangian flow phi, and I might just say that for every point x in A, there is some trajectory which is actually picked up from this regular Lagrangian flow. And in a sense, this is the good trajectory, because it can be bundled all together to form this flow phi, which as a flow should be unique. So this means that if I choose consistently the best trajectories for all points x in A, so the other trajectory which I know to exist, I should get a flow which does not satisfy this axiom that if I take the push forward of the Lebesgue measure through the flow, I get something which is bounded by a constant times the Lebesgue measure. So they're actually, these guys, they're divergence free. So essentially what it happens is that if I take a set of positive measure and I pick up the bad trajectory, the corresponding flow that I will get will for sure violate Liouville's theorem, for instance. And you might recall that we have the stability for these regular Lagrangian flows, which means that if I take any meaningful smoothing of my vector field U and actually follow the trajectories for the smoothed vector field, what happens when I let the approximation converge towards my final vector field is that I pick the regular Lagrangian flow, which means that I pick actually the good trajectories. So the bad trajectories are very shy, and they hide from pretty much any approximation procedure that I might take. So this means that it's kind of a really lucky break that we discovered the bad trajectories. And in fact, it's actually a fact that we were trying to do something else, and we discovered, in a sense, this theorem more by accident. So let me tell you what we were trying to do. So what we were trying to do was the following. So you might go back to the DiPerna-Lions theory for the PDEs, and you might remember that the DiPerna-Lions theory was telling you the following. So take a vector field U which is in W1P, and take a rho which is in LQ for an exponent which is strictly larger than the dual exponent, or bigger or equal than the dual exponent of P. And then, of course, this assumption would guarantee you that U times rho is in L1 lock. And then you would have, by the DiPerna-Lions theory, uniqueness, existence, uniqueness, and stability of the solutions to the transport equations or to the continuity equations. Now, on the other hand, you might notice, of course, and this is pretty clear, that by Sobolev embedding, U in W1P actually guarantees that U is in LP star for an exponent P star bigger than P. In fact, for P less than N, you have Sobolev embedding, but for P larger than N, you even have Morris embedding, which tells you that U is bounded. So to make sense of rho times U, which was the only thing that we needed to do, for instance, for the continuity equation, if P is larger than N, you can take rho which is L1, and if P is less than N, you can certainly do better than this dual exponent of the summability of the derivative, because the function, the vector field U itself, is actually better. So you could ask the following question. You could ask whether the duality between Q and P is actually just a technical condition, and in fact, you should be able to substitute it with the Sobolev improved summability. Or you could even ask, say that I give you some assumptions under which you not only know the Sobolev property, but you know some extra summability for U beyond the Sobolev exponent. For instance, I tell you beforehand that U is bounded because I have some maximum principle, which tells me that from, I don't know, some PDE. Can I then just require the bare minimum for rho, which is that you're dual to this extra summability that I gave you in order to get uniqueness and stability? And in fact, if you go back to the paper by Caravenna-Crippa, you would know that when your P is bigger than N and you look at positive solutions of the continuity equations, then you're actually well posed under the minimal summability requirement, which in this case is exactly rho in L1, because being P larger than N, U would actually be bounded. Okay, so you get a much better theory in that case if you're looking at positive solutions, and you might ask, what is the difference between having a positive solution and a solution which changes sign? And the nice property that you have more than by assuming positivity is what in the current modern theory is actually called Ambrosio's superposition principle. So let me give you a heuristic for this superposition principle. So assume you have two flows for your vector field U, which is not equal to 0, sorry. So this is a typo. Now, if you have two flows, you can take an initial density distribution and push forward it through one flow and push forward it through the second flow, and you get, of course, two different solutions of the continuity equation with the same initial data. Okay, but then, of course, if I take a convex combination of the two solutions, this is a solution 2. Now, Luigi has a very nice interpretation of this, which is probabilistic. It means that in this a convex combination, in a sense, you're taking with probability lambda the flow phi, and with probability 1 minus lambda the flow phi 2. And once you actually take this point of view, what Ambrosio's superposition principle is telling you is that, in fact, all positive solutions can be built by choosing trajectories and random in a sort of similar fashion. So the actual theorem just says the following. You don't actually need any regularity on U and rho besides the fact that you have enough summability to multiply rho and U, and you just need rho to be positive. More precisely, you actually need rho to be non-negative, and to be a solution of the continuity equation with some initial distribution. And then you would know that there is a family of probability measure, eta x, which is indexed with this x. This is a family of probability measure on the space of absolutely continuous curve. And it's a probability distribution on the solution of the ODE that you have. So eta x is concentrated on the set of trajectories of U with initial point x. And now what you would know is a sort of formula which looks ugly at the beginning, but I will explain you with some details, that tells you that essentially this eta x is a probability distribution which is varying from point to point on all possible flows that you can actually take for the ODE. And what you have to do is you have to push forward your initial density rho 0 along all these possible flows and then sort of bundle them all together by using the probability distribution. Okay, so if you look at this formula over here, just to get a better feeling for what it means, if you assume that you are in the classical situation and you have a unique curve gamma for every initial point x, which is solving the ODE, then Ambrosio's theorem tells you that this probability distribution has to be the Dirac mass on that curve gamma. So if gamma is the one which is picked by the regular Lagrangian flow, of course, which is the case for p larger than n, of course, this just means that eta x is the Dirac mass on the trajectory that you get by freezing x and varying t. Okay, so now you can actually substitute this expression inside your formula, and once you do that, you get the an inner integral, which is with respect to a Dirac mass. And of course, when you're integrating with respect to a Dirac mass, you just have the valuation of the function f at that particular point. Okay, and now what you have here, you would just recognize it's the push forward through the regular Lagrangian flow of the measure, which is the initial density distribution times the Lebesgue measure. So this gives you the usual formula which you get from Liouville theorem. Once you know that the ODE is unique for almost every point x, which is the case for p bigger than n by the Jabin Caravenna-Crippa theorem. And so this tells you then that your solution of the PDE is actually uniquely determined by the regular Lagrangian flow. Okay, so now let me go back to again the Jabin Caravenna-Crippa almost everywhere uniqueness, and let me give you a feeling on how you prove it. So you remember that if U is in W1P, then you get you can use an estimate with the maximal function to actually get a Lipschitz type estimate, which is not really Lipschitz because this function f would not be constant. Now, what is actually a classical fact, which, for instance, follows from Morray's lemma when you're trying to prove Morray's embedding theorem, is that when p is larger than n, actually, you can prove an estimate of this type, which is asymmetric, meaning that you just need to evaluate your function f, which is LP, only at one point x, rather than at both points. Now, once you have this, you can go back to actually your proof of uniqueness of the ODEs using Gromov. So remember that if you had a Lipschitz map, then you would have this estimate. If you had a Sobolev, and Gromov would actually give you everywhere uniqueness. if you had the DiPerna-Lions theorem, U would just be in W1P, and you would have this symmetric estimate. And then by what I have with Gianluca Crippa, you would conclude the uniqueness of the regular Lagrangian flow. But now, if you are in P bigger than N, you actually have this function F, which is composed only with gamma of T. And the heuristic would be that if I have at least one good trajectory for which this function is L1, and this good trajectory is actually provided by the regular Lagrangian flow, then since here the other trajectory gamma bar is not entering, I would be actually able to conclude that once I have a good trajectory, almost every, which exists for almost every initial point, any other solution of the ODE in the classical sense would have to coincide with it. And this is how Jabin and Caravenna-Crippa do the almost everywhere uniqueness. Okay, now if we go back to these two inequalities, right? So we have a family of inequalities which depend on P, which is given by this usual estimate with the maximal function when P is less than N. I should have said actually less or equal than N. And we have now this better estimate, which is provided, for instance, by Morray's proof of the usual Hölder regularity, in which the estimate is asymmetric because I have the function f, which is computed only on one of the 2 points x. Now, this is slightly disturbing. You would imagine that there should be a way to interpolate between these two inequalities as I pass with p continuously from 1 to n, right? And in fact, this is what we prove actually it can be done in this paper by Elia Bruet and Maria Colombo. And we prove this version of the inequality, which is actually true for every p, where instead of having f of y on this side, we have a mixture of f of x and f of y. We have a product. And you might actually recognize that when I push p to n, I will actually be able to get this exponent alpha closer and closer to 1, which means that the contribution which is coming from f of y will disappear as p actually approaches n. So finally converging towards this inequality over here, which is true in the range p larger than n. And in fact, we have also proof that the range of alpha is optimal. So now, once you have this improved inequality, you can actually go back to the positive solutions of the transport and continuity equations and show that they are well posed in a range of exponent, which is strictly contained in the DiPerna-Lions range, but it's also strictly smaller than the range of exponents for which the equations make sense. And in a sense, this corollary was not so satisfactory because it left us with a gap between, anyway, a gap which is smaller than the gap between the DiPerna-Lions range and the range in which the equations make sense, but nonetheless is a gap. And that's when we started just wondering whether this is just a technical limitation or it is in fact that it might be that there is ill-posedness for some range of exponents for the PDEs. Now, if you go back to this conclusion that we had using Ambrosio's superposition principle, you might remember that the almost everywhere uniqueness actually gives you the uniqueness for positive solutions of the continuity equation. So this was the argument. So if we produce actually an example of non-uniqueness of positive solutions of the continuity equations in some range of exponents, since Ambrosio's superposition principle is always valid, we would actually have disproved the almost everywhere uniqueness of trajectories. Okay, and that's in fact what we do. So we have a theorem with Elia and Maria, which says the following. So for every p which is less than n, we can cook up an additional summability q and a corresponding dual exponent q prime. And then we can get a vector field u, which is in W1P, intersected with this LQ prime, which is divergence free. A rho, which is in LQ and which is positive. So a rho, which is in LQ, the dual space of LQ prime, so that I can multiply rho and u. And this rho is actually going to be a solution of the continuity equation, starting with the initial data rho at time 0 equal to 1, but such that the points where rho is not equal to 1 has positive measure. And now this should ring a bell because since the divergence of u is equal to 0, this is actually what I'm assuming over here, the function rho bar, which is identically equal to 1 at all times, actually solve the equation dagger because here I would land with divergence of u times 1, which is equal to 0, and time derivative of 1, which is equal to 0. So, but since actually the solution that I've produced in this theorem is different from 1 on a set of positive measure, it turns out that rho and rho bar are actually two distinct solutions. And now, since I actually got two distinct solutions, Ambrosio's superposition principle tells me that for this vector field u, which is in W1P for P less than n, and is divergence free, there cannot be almost everywhere uniqueness of the classical trajectories of the ODEs. Okay, so these solutions are actually generated by convex integration, which is a method which has been used in geometry to produce a lot of counterexample, a lot of counterintuitive solutions to partial differential equations and inequalities, which are related to differential geometric problem. But in fact, the way I've presented actually this theorem would be rather dishonest, because it is not that we discovered the failure of uniqueness in the full range of possible exponents. This was actually something which was discovered in a beautiful paper by Modena and Laszlo Zekai-Hidi in 2018, where they proved the previous theorem for P less than n-1 and for sign changing solutions. And this paper was actually improved last year to get the previous theorem in the full range, so P less than n, but again with sign changing solutions. And this was done by Stefano Modena and Satich. So now let me just remark that the real contribution of our theorems was actually to get these solutions to be positive. And this is especially non-trivial in the range of exponents which goes between n-1 and n. And in fact, a feature of our argument is that this is considerably simpler than the Modena-Satich theorem. And so even when we actually revert to the sign changing solutions, we get a new proof, which is much easier to follow. Okay, so I don't have actually time for the last couple of slides. I just wanted to say that these convex integration solutions have an history which has been developing in the last 15 years, and especially in fluid dynamics, started with some works of Laszlo Zekai-Hidi and myself. But let me skip on this, which is more like, for the records, and which can be easily seen from the slides which will be available from the web. And let me actually conclude this proof, this talk by thanking you for your attention.